this first presentation. We have Greg, Nicholas, Micah, and Davor. If you can give them a round of applause as they make their way up to the front. Now, some of you might be wondering, none of these look like Jim Keller, right? None of them look like Jim Keller. Unfortunately, close enough. We did get I got a text from his executive assistant this morning saying he had an emergency come up. He wanted to be here. He's excited about the mission. And yes, he's going to do a podcast with us to record to make up for it. So we're excited. We have Davor, who came this morning, subbed in for him, and we're thankful for it. We also had Raja. Raja, who was supposed to be here as well. That's not Raja, but Raja was supposed to be here. Raja woke up with he was sick this morning. He had some kind of virus and wasn't able to make it either. And so Micah has subbed in for him. So I'm grateful for the subs that we have, and I'm grateful for everybody who's here. So what we're going to talk about during this session is the past and future of compute, and more specifically on software architecture, the birth of software architecture, and the past of it. And I'd like to start here. If you can give your name and a quick 60-second overview of your experience with software, compute, and even CUDA.
Okay, let's see if the mic works. Okay, thanks, Jeff. I'm Greg. Let me tell you a little bit about me. So back in 2005, I interned in John Nichols' CUDA architecture group at NVIDIA, and he convinced me that CUDA was the future. Based on that, I built Ocelot, which was a backend for CUDA that targeted all sorts of different accelerators. It included NVIDIA, Intel CPUs, Knights Landing, and AMD GPUs. After that, I went back and worked at NVIDIA. I worked on software architecture. I was on the first deep learning deployment in CUDA at Baidu. We built a 4,000 GPU cluster, and we trained, at the time, the largest neural network in the world. We built the first framework. We invented collectives. We discovered scaling laws, which led to all of the progress that we've seen today in LLMs. And yeah, I'm very opinionated about how you can build AI applications on top of GPU accelerators.
We're excited to hear about it. Thank you, Greg. Davor?
Okay, I'm Davor. So how I got into parallel computing, I was doing my PhD at University of Toronto. And basically, in the grad studies, at that point, there was already GPU's first version of CUDA came out. There was also IBM Cell. There were talks about Larrabee and even the future roadmap for Knights Landing, and there were FPGAs. So at that point, it seems that the future of parallel computing is going to be very diverse, and we're going to have lots of programming models and lots of architectures. We all know how all that panned out. I spent some time later at Altera working on making FPGAs more programmable, more accessible. Then Altera got acquired by Intel. And then after that, I went to Tenstorian, and I'm there now, which is an AI accelerator that we think is the future. I mean, a part of the future. I don't think future is singular. I think future is definitely diverse. Just the question is, who's going to be part of it? Yeah.
Exactly.
Hey, my name is Micah Villmow. I'm the chief software architect at a stealth startup. Here is just the front. I got started with AI back in the 90s. Some of you might have heard of this project called OpenPsych. And I thought that was really cool. And so then when I went to college, I started teching out. And I got a phone call from some guy named Vineet Goel in ATI Graphics Orlando. So I'm on the AMD ATI side while they're working on the CUDA side. So I got to do fun things like CTM, Cal, Brook Plus, OpenCL, HSA, all the same while they just worked on CUDA. CUDA. After that, I did some startups that Intel bought a startup, and I didn't want to go to work at Intel, so I went to work for NVIDIA, because why not? AMD at that point was now on HIP or ROCm, or I forgot. And so after 7.5 years at NVIDIA, I figured CUDA's not the final answer. It can't be. Otherwise, what are we doing? So I went and joined a startup working with Raja Koduri, and we're designing hopefully what we think is the next thing after CUDA.
Hey everyone, Nicholas Wilt. I was on the inception team for CUDA at NVIDIA. Work started in early 2005. I was the architect of the driver API, which is sort of the bedrock software, portable across operating systems and CPU architectures that enables CUDA to run in all the different contexts where it can run. And I wrote the CUDA handbook, copyright 2013, and a second edition is long overdue.
Awesome, thank you. To start, Greg, you and I had an interesting conversation over dinner a couple of months ago, and you were sharing a bit of the history of CUDA and how it got to where it's at today, and it went from, being a project to being brought into NVIDIA and then becoming cool. Ian Buck became, made it cool, and then, got it to where it's at today. Why do we consider CUDA to be NVIDIA's moat? And maybe you guys can all share your perspective on that.
It's a good question. I think the software stack is a huge piece of it. It's not the only piece. I do think that the move from multi-core to massively parallel accelerators and SIMD is an important piece. Like building a high-end, leading-edge processor today that's this high performance is extremely difficult. But I really think the core piece of it is the software stack. One tidbit about the software stack, look at the kernels. Like look at Cutlass. Look at how you were able to get near peak utilization, 80, 90% of peak utilization across a variety of workloads. If you haven't looked into the details of how that gets made, imagine hundreds of people looking at pipeline latencies, doing cache blocking. It's extremely labor intensive and extremely difficult to replicate that. It's easy to do great on one workload, but it's very difficult to do well on a breadth of workloads. And I think that piece, the Cutlass piece today, is an important piece of the moat.
Anybody else have any?
Yeah, and I think he's right. It is the software. But it's not just the software. It's the software in sync with the hardware. You can't just take CUDA and stick it on some other random hardware and expect to get performance. Because the programming model, the SIMT programming model that CUDA defined, that was revolutionary. And that architecture came out, and AMD had its own programming model, but it wasn't fully defined, fully formed. But when you have that software, hardware in sync and the architectural level, that's the moat. Because sure, you can replace some pieces of the software, but you have to do it for hardware that works correctly.
So I've had the opportunity to debrief early CUDA history with would-be competitors, and I think NVIDIA deserves a measure of credit for being willing to take the die area risk that they did to build CUDA in the first place. And then in Volta, there was about a CUDA-sized risk, again, taken to keep machine learning clock cycles on their devices in the form of tensor cores. And the fact that the software is portable into so many contexts, I think is an underappreciated reason for CUDA's pervasiveness, because it enables NVIDIA to explore design spaces. They did a brief foray into, power with cache coherency with Pascal and Volta devices, and I think if the software weren't so portable, then those types of speculative risks by NVIDIA would not have been possible. And that's a property of the software that's durable as long as they, keep up the care and feeding of the software as they can. It's the type of investment that is hard to retrofit into a code base.
So, there are a couple of pieces to the puzzle that you guys mentioned. So yeah, like the software and hardware need to be co-designed and really in sync and work great. They definitely did an amazing job there. It needs to crush on the benchmarks. Like NVIDIA invested so much into MLPerf and deep learning benchmarks, and before into HPC benchmarks. So this is this is not strange to them. And then it has to be general, right? It was general because it worked for HPC and other applications. So I think, and they paved the path. They did invest into CUDA. They just showed we can build something that is sort of domain specific. It's not C++, right? It is a narrow language in a sense, even though it's general. But ultimately, now all of the new accelerators that are coming up in architectures, like, do not need to reinvent all of this. For example, a coprocessor, a heterogeneous program model where you have PCI Express adding card, and you have host APIs, and you have device-side APIs. CUDA has paved that, so you just basically, that's a good template to take it, right? And in Storm, we're doing the same thing. There's host APIs that are similar to CUDA. There's device-side that are similar to CUDA. So I don't think everything is getting sort of reinvented or changed, right? Anybody who can deliver on a good hardware, software co-design and benchmarks will do well, ultimately. And they will, some folks will be in the super high performance, some in low cost, some in the great per dollar. It's a huge design space, but I think there are these three key pieces or four, let's say, that you need to check mark in order to be successful. Have a general purpose programming model, co-design, hardware, software, benchmarks, and then anybody who does that will definitely play a part of the future. So I think it's totally different, a totally different era now. And especially with LLMs, like someone said, oh, how are we going to port all of the Triton that OpenAI wrote to like architecture? I'm like, I think LLMs will have no problem translating that soon.
Yeah. And on that note, where do we see the opportunity to overcome? Is it even worth the work it's going to take? They talk about the 10-year gap or the 18-month gap that exists. Where are the opportunities to overcome the CUDA moat?
In my view, it's usability, generality and usability. Even today, setting up and running models on NVIDIA is hard. It's difficult. That's why there's companies that you can pay to do it for you. But that's because CUDA was designed for a different age. And I think it's at the peak of its course, but it's going to run its course. So we need something that's general, usable, and developer-friendly. If you go talk to people come out of school, they don't know C, C++ at all. They don't talk to them about pointers, and their head explodes. You need something that's more friendly for developers. Once you get in the developers' hands, there's your backdoor to success, because that's how NVIDIA got CUDA everywhere. You have classes that taught the developers. The developers, as he said, went to other companies. Like he took CUDA to Baidu, and then had the first GPU build out. Get something usable for the developers, and right now it's all complicated. So we need new languages, new programming models, new system architectures, hardware, software. We need the whole thing. And
yeah, I agree with that. Like, for example, like towards, let's say, again, going back to in grad school, at some point we were learning like Fortran, OpenMP, pthreads, everything, right? All the program models that were out there. And then by the end of the grad school, it was only CUDA, because basically got hijacked. The whole like academic, basically parallel programming, distributed computing was just CUDA, right? It became synonymous. So if you know CUDA, you're a parallel programmer. If you're a parallel programmer, you're CUDA. But that is not just due to CUDA. Like if there were other architectures and program models that delivered on performance and usability and a good software stack, they would have entered the arena. It's just happened to be that everybody jumped on with the only thing that kind of worked, right? And it still has issues, right? But he said, but there is a stack of, right? There's folks who just want to know PyTorch. They don't care if it's an accelerator, if it's Trainium, TPU, JAX, right? If you started JAX, PyTorch. And then there's high-performance libraries, like Cutlass, right? Then you're a little lower level. You already know how to use a high-performance library. And then at the bottom, it's CUDA or the actual bare metal program model. So there's at least like 3 layers that even in CUDA were essential, right? Without Cutlass and cuDNN, a lot of folks would have to rewrite everything if the things didn't work out at the PyTorch level, right? Yep. So they kind of went down one level, and then they used that. So I think those are three pieces in any successful software stack. The bare metal program model, libraries, and then PyTorch JAX seamless integration, right?
So let me think about it from a machine learning application perspective. I think the real opportunity for beyond CUDA is applications that are beyond CUDA. I think there have been a few pillars that have really, NVIDIA found them in the early days of deep learning, and they've really been mining them successfully. So one is tensor cores, which is the foundation of CUDA, massive parallelism, structured parallelism, low precision. Another one is just the network. The NVLink, InfiniBand scale out to massive training, so being able to train models on tens of thousands or hundreds of thousands of GPUs. And then we're starting to explore sparsity. So we're starting to explore structured sparsity, fine-grained sparsity, and mixture of experts. Those are the tracks that NVIDIA has optimized their system for. And the real opportunity are applications that are not on any of those tracks, that would require a different type of system optimization that NVIDIA, because of their success, they cannot take because they would have to abandon one of those pillars. And it's worth noting that all of those pillars are at the top of their S-curve. How much lower precision are we going to cram out, like extract out of 4-bit? We're going to go down to 1-bit. We're actually going to go down lower than 1-bit. But they're getting to the point of diminishing returns. So I think the time is actually right for new applications that think of a different dimension other than the ones that I just mentioned that really could be the foundation of a new type of application.
So I think one of the challenges is just that the state of the art is still advancing so quickly, and NVIDIA is the platform of choice for people advancing the state of the art. And if it even slows, or if verticals emerge where we actually understand exactly what we need to do to service the types of application Greg is talking about, that's the most obvious opportunity to me.
But it's interesting, exactly as you said, like things are still evolving. So things are getting co-evolving, right? Like AI applications are co-evolving with the accelerators. But your first edition of your first book, right? It was sort of basically SIMD, right? Signal instruction multiple thread. But then what is CUDA today, right? Like when you wrote the book, there were no tensor cores. There was no NVLink. There was no NV switch. There was no like nickel. Is nickel CUDA? Does it really fit into SIMD? Nickel? Not at all, right? Basically, this was even prior to cuDNN, and there were no tensor cores. There was no tensor memory accelerator, TMA. So basically, anything NVIDIA does is a kitchen sink. Just throw in and call it CUDA, right? Like, is nickel really CUDA? It's not even a CUDA program model. It's more like MPI, right? It basically is an MPI knockoff, right?
I think CUDA has always been building, and they're adding more things to it. And I feel like today, when we're talking about CUDA, we're talking about the collection of everything. Actually, this is a funny historical note. Go back and look at maybe in like 1990, there was a company that was called MassPar that built the a Fortran version of CUDA. So even you could imagine CUDA C is a something that's built in an innovation that's adapted on top of a SIMD massively parallel execution model.
And yeah, it's just since you mentioned MassPar, we should take a moment to recognize that John Nichols, whom you mentioned earlier, was a co-founder of MassPar, and he's the one who brought all the secret sauce to NVIDIA to teach them how to build compute hardware.
Does anybody have a question from the audience that they would like to ask? I want to ask one question. Stand up.
As James Tandon, Cassia AI. There are probably 100 or so companies right now who are trying to build AI chips, AI hardware. It's the gold rush. But one nice thing about CUDA with NVIDIA is that it's very highly tuned to NVIDIA hardware. If we try to build another accelerator, it's not going to be very good to compile the CUDA code to that new hardware. As a result, because of the diversity of chips, we're going to have a diversity of requirements in the stack. So what are your thoughts on bringing consensus to the software stack for all these different hardware accelerators?
I actually think that the AI world has came to a consensus on what it should be, and it's mostly NumPy-based Python. Now, you don't have to like it, and I know there's companies that are trying to figure out better ways of doing that, but if you can write NumPy-based Python code and it compiles to your accelerator either through PyTorch or JAX, you don't have CUDA problems anymore. What the problem is everyone else's code. because they wrote it for CUDA. And they put CUDA-specific assumptions into it. But if you're writing the code yourself and you have an accelerator like Davor does with Tenstorrent, they have a whole software stack that you can use today and get performance. But it's how you get the CUDA code, the CUDA ecosystem to run on your accelerator. That's the hard part. And that we need some kind of solution to do. We need that bridge from where we are to the future. And I don't know what that bridge is. I don't see it being developed, but it could be out there. Maybe someone else knows.
Like you're referring to like an actual code base of CUDA kernels? Because if your code is in PyTorch, there's compilers that automatically take and compile to the accelerator, like PyTorch 2.0, for example, right? It compiles to a variety of accelerators, so that is CUDA agnostic, right? In order to be able to go to PyTorch 2.0, or JAX compiler, XLA, right? So then you're talking about like porting cuDNN or Cutlass, or raw actual CUDA kernel. And there's PTX ultimately at the end of the day, at the bottom, or even SAS, right? So so it depends which part.
And we have time for one more response if somebody wants to respond to that then.
Well, just a perspective, I think, Micah, it's kind of related to what you're saying of like the hardware, software co-design. Back in the day, I think when PTEX came out, there was a hope that it could be performance portable. So it's functional portable, but there's a hope it can be performance portable. The reality today is that even on NVIDIA, we compile separately and we tune and optimize separately for every single device architecture. So I don't think that that's going away.
Yeah, so basically like ultimately if you're tuning even for different flavors of the GPU, and then you have an Intel GPU and AMD GPU, so if all of those are basically different now, and it's a different style of PTX, I don't think you can rely that to just keep like one thing, right? So basically I would just abstract it into parallel programming, distributed systems, and concurrency, and then if basically education of the developers is back to just those first principles, they will be able to easily navigate between, in Tenstorrent we call it Metallium program model, or PTX, or ROCm, right? I don't think that'll be a problem, especially with AI-enabled tools, either pair programming tools like Cursor, or just AI actually translating a PTX code directly into another low-level code, right? I think these are all around the corner, and I don't think this will be an issue at all very soon.
Awesome. Well, I wish we had more time. Let's give our panelists a round of applause. And thank you so much. You guys can go ahead.